Wanted to slide the refrigerator. 0.4 times 200 pounds. This one ought to be not much to this one. The force necessary to make it slide is 0.4 times 200 pounds. You're not going to get it going with any other force than that. It's 80 pounds worth of force. Now the question is, will the refrigerator tip over, or will it go ahead and slide like you want it to? Well, notice that the force is 4 feet above the floor. Let's just show that the refrigerator is slightly tipped. That's a greatly exaggerated view. I wouldn't push it that far before I realized I was in trouble. Put the load P on it, 80 pounds. That's 4 feet up. Here's the weight of the refrigerator, 200 pounds, and that is a 3-foot wide refrigerator. That's a 1.5 feet, and therefore you can sum moments about this right corner of the refrigerator. If 80 times 4 is bigger than 200 times 1.5, then you're not going to be able to move the refrigerator. You're going to either have to wax the floor, or you're going to have to bring this P force down to a lower level. What's 80 times 4?
320.
And what is 200 times 1.5?
300.
It's not going to work. This overpowers this, and therefore it will tip. You'll never get the refrigerator in its new position at that rate unless you don't mind having it there like that. Alright, pulleys. Pulleys are really simple if they are frictionless and have no mass, and that is the assumption made in most of these. If it doesn't have any mass, then it doesn't have any tendency to not want to roll whenever you want it to roll. And if there's no friction, then the force on this side, since it has this moment arm, is the same as the force on this side, since it has the same radius. Now if you make a pulley like this, well, then the forces on both sides wouldn't be the same, but that's a pretty bad pulley. So anytime you see any force known on one side, you can assume it comes out the other side. That also means that the force in this wire is 2 F's or 2 W's. Here you put an F, so on this side you have an F. This weight is 2F. Here's a whole bunch of them. If this is F, then this one's F. And if that one's F, then this one's F. And if that one's F, then this one's F. And if that one's F, then this one's F. You can just follow them around. Now if you want to know how much is inside right here, then how much inside of here is 2F. The reason being, if you look at this pulley, an F is pulling up on the pulley and an F is pulling up on the pulley. That's 2 F's pulling up. The pulling down on this pulley must be 2F. And all the rest of them work the same way. So, as an example, we have a set of pulleys, and let's just say that this thing with the handles on it here weighs 600 pounds, and I would like you to tell me how much tension there is in this rope right here. Well, if there's T in this rope, then there's T in this rope. If there's T in this rope and T in this rope, guess how much force there is in that rope? Well, you look at this pulley, you see T up and T up, it has to be 2T. Now you can check that further. If this is T and this is T, this must be 2T. If this is T and this is T, then this must be 2T. If this is T, then this must be T. That works out okay on this pulley here. You'll notice T down and T down. It's balanced by 2T up. And now then I can tell you what's holding up this can. This can is being held up by a T and a 2T. It's pulling down with 600 pounds. The tension in the rope is 200 pounds in the rope. So pulley problems are almost a gimme. Here's another one. If P is 80 newtons, how much does this block weigh? If this is 80, then this has to be 40, and this one has to be 40, because that's the only way these two can hold up this 80, half on each side. If that's 40, then this is 40. If that's 40, then this is 40. If those two are 40, then this one is 80. If that one is 80, then this one is 80. If those are 80, this is 160. This thing weighs 160 pounds. And here's one kind of like a real one. If the weight is 1,200, well, but I don't know how much comes on each end. Let's just start here. If this is T, that's T. If that's T and that's T, this is 2T. If that's 2T, this is 2T. If that's 2T and that's 2T, that's 4T. If that's 4T, that's 4T. If that's 4T and that's 4T, that's 8T. If this one's 4T, this one must be 4T, this one must be 8T, and 4T and 8T are holding up this block. 12T, 1,200, answer. Okay, this one's going to be similar to the same thing. If this is 1,000, then this is 1,000. You'll draw a free body of this connection. Here would be that connection. You'd show 2,000 newtons down. You would show 1,000 newtons up at a known 45 degrees. Here you have an unknown force and an unknown angle. You'll notice if the angle up there is beta, then the angle down here is beta. This would be 90 minus beta. Its magnitude would be answer. Some forces horizontal, as we've been doing, using this and this in your equation. Some forces vertical, using this and this in your equation, and of course these guys too. You have two equations and two unknowns. One would be the force, one would be the angle. You might want to practice with that one. It's more math than statics, because somewhere around here you're going to get something that says something times the cosine of something and something times the sine of something. You're probably going to have to take sine of something over cosine of something so that you can get an answer for the tangent of that angle, and then solve for the angle. Alright, friction also goes around pulleys. Except pulleys are supposed to pull, so I think this really more likely ought to be called a drum or something, a stationary drum. Every now and then you'll see they'll still say it's a pulley when it's locked up. It's not really a pulley. Here's your equation, everything you need to know on how to solve for these forces. First off, one side or the other will be a known number. For instance, this may be 60 pounds because it's a 60-pound weight or something like that. The 60-pound weight goes around, or the force goes around the drum, and here's a guy trying to pull down on it and lift this weight. He wants to know how hard he'll have to pull, and he'll have to pull pretty hard because there's friction around the drum. The equation for F1 in terms of the known F2 is in your text, or in the reference manual too. It's F1 is equal to, take the known F2, on your calculator, raise E to the coefficient of friction to the angle theta in radians, and that'll tell you how hard you got to pull on this side. So an application of that, I think this one came out of your book. You'll notice they call it a pulley. Now that's confusing. I would hope they wouldn't do that on a quiz. If somebody asked me how hard you got to pull, I'd say this is the only thing that matters. If it's a pulley, it's not supposed to have any friction, and therefore it couldn't have any friction along here. So this is a stuck pulley with a 35 centimeter diameter. The equation for how much force F1 you have to pull on this block can be found, because you know the coefficient of friction is 0.58. You know the normal force is 150 kilograms, that's not a force, times 9.81 meters per second. That's now in Newton. Multiply that for me if you would. You'll notice I now put the friction arrow on there resisting motion. How much did that come out?
1472.
Thank you. 1470 newtons. This friction force right here is 1470 newtons multiplied times 0.58 for the coefficient of restitution. That block will not slide unless you apply a tension force on the rope of
852.6.
850 newtons. Therefore, this has got to be 850. Now, the only question is how hard does this guy have to pull, since there is some friction around that drum? The equation is the same as before. F1 equals F2. F, in our case it's F, is equal to, which side are we on? We're on the, got to make sure which side you're on. I'll say F1 is equal to F2 times E to the coefficient of friction times theta. And we're on the loose side, and the loose side is the F2 side, so that's where we put this. So we put 850 right here. We can tell if we're getting the right side. If we got the wrong side in here, it won't be hard to tell, because it'll be easier for this guy to pull than it was for this to pull, and that's not just destined to happen. Alright, so we multiply 850 multiplied times E, get E on your calculator, raise it to the 0.58 times, oops, now we've got to get theta here in radians. Well, he gave us theta, but he didn't give it to us nice. He gave us 60 degrees. So raised to the 60 degrees times 2 pi for every 180 degrees, and whatever that comes out. That's how hard you'd have to pull. Did you give me a number already? It doesn't matter. I don't care. Anybody can do that. How big?
6,900.
6,900? Sounds a little big. We could check in the book. The answer's in the book. Doesn't matter, but I don't care. But let me just say, well, it might be that big. But anyway, and newtons. Check that number. Looks a little big. Will the block move? All right. Will the block move? Well, the block will move if the big coefficient of friction has enough power to stop the 150 kilogram mass from unsticking between what's on his head and what's underneath him. So first off, let's take a look at the 100 kilogram mass. It has 981 newtons of force, and therefore the pressure between that block and the 150 block is also 981. He's being held to the left, and since the 150 kg block is sliding to the right, the friction force on his bottom will be pulling to the right. And that will be, if it sits still, 0.3 times 981 newtons of force. How much is that? While you're doing that, I'm going to draw a free body of the 150 block. What is 0.3 times 981?
294.
294 newtons worth of force. That means on the top of the 150 block, there is also 981 worth of pressure on his head, and the friction force, since it's on the other side of this plane, will go the other way, and that is 294 newtons. That's if the block is just ready to break loose. Now, the block itself doesn't weigh 150 kilograms, weighs 150 times 9.81. This block weighs 1,472 newtons. And therefore, the pressure on his bottom is 1,472 newtons plus the guy sitting on his head, 981 newtons, for a total pressure between the lower block and the floor of 2,453 newtons. That means that in order to slip by being pulled with a force P of 900 newtons, the friction force would again be 0.3 times this normal force, 2,453, which is equal to 736 newtons. And if 736 newtons plus 294 newtons is bigger than 900 newtons, then 900 newtons won't break it loose. Is it?
1030.
1030? Okay. The answer is no. Now that's not likely, a question like that's not likely to occur on the quiz. That came out of your book, I think. And the reason I say that, it may not have, it may have come from someplace else, but that's a yes-no answer, you know, and they always have 5 parts, so they're not going to be able to fit a yes-no question in there. More than likely, they would ask you, how much force would it take to break the blocks loose? And then the answer is 294 plus 736. That would be how much force it takes. Same way with this one here. Will the block move? Looks like I thought that was a nifty problem because that's all my writing. That won't be on a quiz because it's a yes-no problem. Let's just change it right quick. How much force does it take to get the block to move? Then he can write you down 5 answers, 4 of which are wrong. The question is, will the block move? If the answer might be no, then it is not moving. If it's not moving, this is the one we want. We want the big one. And here is the force underneath it. The force underneath it is 600 newtons. You'll notice I don't have to multiply it times 9.81. That is a force with newtons. Plus, there's some more force P pushing down on this guy's head. Since this is a 3, 4, 5 triangle, check it out, then 3/5 of P are acting down. If 3/5 of P is acting down, let's see here. What am I getting ready to do now? My sum forces in the horizontal direction. I'll need this friction force. This friction force is 0.4 times 3/5 of P. I forgot my 600 plus 600. So there's the possible friction force. And all right, let's calculate. We've already summed forces vertical here to get this. We used that fact to get the friction force. Here we're going to now sum forces horizontal. Sum forces horizontal is equal to 0 is equal to 4/5 of P acts to the right minus the friction force acts to the left, which is 0.4 times 3/5 of P plus 600. And one equation and one unknown, we ought to be able to solve for P. And that's what we were doing right then. See what was going on. Comes out 429 pounds. Alright, that is the end of this tape. If you would go to the next tape now, we'll continue